Today we're going to solve another problem, and again we're going to use our knowledge that we have gained about second derivatives and concavity on functions. So this is going to be an optimization problem, and we have here a metal container with an open top, and we're asked to find the dimensions of the container such that the volume would be 4 meters cubed, and we would use the least amount of sheet metal as possible, so the area has to be the minimum. So let's just jump right into it. Okay, so first of all, the volume. The volume for a rectangular container would be x times y times z, and that would be equal to 4 meters cubed, but here z, since it has a square base, would be x, so the volume would be x squared times y, and this is equal to 4. Now, what about the area? Since we're looking for the minimum area, we would have to find the first and second derivative of the area with respect to a variable. So the area would be x squared, the area of the base, plus 4 times xy, since we have 4 sides, since remember that it has an open top. Now what we can do here is we can express y in terms of x, so we can take the derivative of the area in terms of x. So if we go from the equation for the volume, we can say that y is equal to 4 over x squared. And we can replace it here. And then for the area, we will get x squared plus 4x 4 over x squared. Okay, so let me just delete this. We'll continue up here. So the area would be what? X squared plus 16 over x. So this is our area, and now we need to find the first and second derivatives of the area. We need to find the first derivative in order to find the critical points, and then the second in order to see about the concavity of functions and where it's increasing and decreasing. So the first derivative would be 2x minus 16 over x squared. Now, since we're looking for the critical points, the derivative has to equal 0 or has to be undefined. So where does this derivative equal to 0? Well, we can say it as equal to 0, minus 16 x squared is equal to 0, and what we can do is we can multiply both sides by x squared. I don't know, we can have here a common numerator, so we'll have 2x to a third minus 16 over x squared is equal to 0, and then if I multiply both sides by x squared, this will be gone, and I will have 2x to a third power is equal to 16, and x is equal to 2. If I divide both sides by 2 and then take the third root of 16. Of 8. After I divide by 2, the third root of 8. So when x is equal to 2, the first derivative is equal to 0. And what about when it's undefined? Well, when x is equal to 0, the first derivative would be undefined. So these two are our critical points. Now what about the second derivative? If I take the derivative of the derivative, I would get 2 plus 32 over x to a third. Okay, now, since we're looking for the minimum area, remember what we studied about concavity on functions. Since we're looking for the minimum area, this would be the concavity would open upwards. So basically we're looking for the points where the second derivative would be bigger than 0. Okay, so since this is a concave up, which points from these two equal the second derivative to be bigger than 0? Well, if you replace the x with a 0, the second derivative would be undefined, so x cannot be the point, so that leaves us only with x is equal to 2. And if I replace in the second derivative formula if I replace x with a 2, we'll get 2 plus 32 over 8, which would be equal to 6. So when x is equal to 2, we have our minimum area. So this point right here, x is equal to 2. Okay, so we have our first dimension. We can find the other two. Okay, so x is equal to 2. What else do we know? Well, since it is a rectangular container with a square base, z would also be equal to 2. And what about the height? Well, remember that we said about the volume is equal to x squared times y, since x is equal to z is equal to 4, and y would be 4 over x squared, which is equal to 1. So we have our dimensions: x is equal to 2, z is equal to 2, and y is equal to 1. And this is our final solution.